Hello friends, myself Shubholokhi Chakraborty from Department of Computer Science and Engineering of Uemk, Kolkata. So today our topic of discussion is data communication, and I would like to emphasize on a particular chapter, data and signal. So we know that basically data needs to be converted into signal when it is passed through the physical layer. So basically there are different types of signal: analog signal and digital signal, and we can see from the diagram that the left one shows the analog signal and the right one shows the digital signal. From the definition we know that in case of analog signal, the amplitude is varied with respect to time. So we can see here the amplitude is varied with respect to time in case of analog signal, and in case of digital signal the amplitude is varied in case of with respect to time, but it is varied up to a certain levels. Right here there is three number of levels. So if the number of level is 2, then that type of digital signal is known as the binary signal. If the number of level is 4, that is known as 4-array digital signal, like this. So number of level can be in the form of 2 to the power n. Right now, so I will first come to the analog signal part. It is two types of analog signals are there. One is the periodic signal, another is the aperiodic signal. So in case of periodic signal, this is the example of periodic signal. This is a basic sine signal we have. Any kind of periodic signal, or rather any kind of signal, there are two parameters to check this signal. Number one is the amplitude of the signal. This is the amplitude of the signal. Another is the time period of the signal, or period of the signal. Okay, so what is the unit of the amplitude is generally volt, and the unit of time period is second. Now we can also calculate the frequency of the signal by calculating 1 upon t, that is inverse of the time period, right? So this is the relation between the frequency and time period, and we can face different problems out of this equation. So this is the table which shows the different types of time period and frequency, and we can see that second, millisecond, microsecond, nanosecond are the different units of time, and here also we can see hertz, kilohertz, megahertz, gigahertz, terahertz are the different units of frequency. Now, so it's a simple example of two sine waves. The first one is having much higher peak amplitude or amplitude, and this is the pictorial representation of another sine wave with much lower peak amplitude or amplitude. So these two are the two types of representation. So let us have one simple problem related with frequency time calculation. So if the time period of the signal is given 100 millisecond, we need to calculate the frequency. Okay, so we have dealt these types of normal problems in the earlier classes, but this to recap all these things. Let's see, is the time period is 100 millisecond. We convert this 100 millisecond into second, and whatever the second we are getting 10 to the power minus 1 we put here to evaluate f. Okay, and we need to convert this one in terms of kilohertz, and the answer is 10 to the power minus 2 kilohertz. So the second problem is to calculate the phase in radian and degree both. So it is given that offset is 1/6 cycle with respect to time 0. So the cycle is 360 degrees, so 1/6 means it will be 60 degree, right? So 60 degree is normal value in degree, and if you want to convert it into radian, we multiply 60 with 2 pi by 360, and the value will be pi by 3 radian. Okay, you can have the calculator to calculate this one. Next we are coming to a simple relation, and we have learned all these things in school level physics, the relation between frequency and the wavelength. So wavelength is basically in one time period how long the wave propagates in one direction, and this relation shows lambda equal to c by f, where lambda is the wavelength and f is the frequency of the signal and c is the velocity of the light, that is 3 into 10 to the power 8 meter per second. So you can face different types of small 2 marks problem from this. Next we are coming to a simple relation, that is the time domain and the frequency domain representation of a simple sine wave. Okay, so the first picture shows a simple sine wave with an amplitude 5 volt and the frequency is 6 hertz, right? So if I want to convert this time domain representation into frequency domain representation, basically we have to see at which frequency the signal is propagating. So if it is 6, so in the frequency domain representation you have a line spectrum here at the frequency 6 with an amplitude, whatever is the amplitude of the sine wave, with that amount of amplitude you have a line spectrum if it is a simple sine wave. Okay, so this is the way you just convert this time domain into frequency domain. Basically if you have a periodic signal, we know that Fourier series is used to convert the time domain into frequency domain. If it is a periodic type of signal, we use the Fourier transform to convert the time domain into frequency domain signal. So this is all about. Now realistic type of signal is the voice signal, and which is not a pure sinusoidal signal, which is basically a composite signal, and we basically can categorically say that this composite signal is a superposition of different simple sine waves with different frequency, phases and amplitudes, right? So this is the example of the 3 sine signals with different frequencies 0, 8 and 16 here. And so if I want to get the spectrum of this combination of 3 signal, we will have the 3 line spectrum, each denoting for the each signal. Okay, so this is all about the 3 signals we have, having the 5 amplitude 5, amplitude 10 and amplitude maybe whatever is the value. This is the thing, and you have the 15 amplitude, and you can see that the signal with 15 amplitude is basically not a sinusoidal signal, is a DC signal. So if you have the frequency 0 means it defines a DC signal with frequency amplitude 15, you have the frequency the 8, and it's all about to calculate. The frequency is not given there, it is given here. So for the frequency 8 is having an amplitude 10 and frequency 16 is having an amplitude 5. So why I have told earlier that, so if it's a periodic signal, we used to do the Fourier series transformation, or if it's a periodic signal, we do the Fourier transform to calculate the frequency domain representation. Now come to this part, I just emphasize on this. If it is a periodic signal, we have seen that it will be a line spectrum kind of, but if it's a non-periodic or aperiodic kind of signal, you will get a continuous spectrum. Continuous spectrum we are going to observe here, that is there is no discrete points, it's a continuously the amplitude spectrum is changing, right? Now another important time in terms of signal is, first we have learned the time period, frequency, amplitude. Another is the bandwidth of the signal. We know that if it's a composite signal, so whatever is the highest frequency and the lowest frequency, the difference between the highest and lowest is basically the bandwidth of the signal. Okay, so for the two example, the first one is the discrete frequencies, the latest series of line frequencies, and the second spectrum is basically the continuous spectrum. For this is the example of non-periodic, and this is a example of periodic. So if I find out the bandwidth, we know that from the definition of bandwidth is the difference between the highest frequency and the lowest frequency, and the highest is 5000 and the lowest is 1000, so the bandwidth is 4000. For the second one also, even if it is a discrete spectrum, it's a continuous spectrum, but the bandwidth remains the same. So there are basically two examples, two questions rather. So first question is that if you have a periodic signal which is decomposed into 5 signals with frequencies 100, 300, 500, 700 and 900, what is the bandwidth? Okay, so from the definition we know the bandwidth is basically the difference between highest and the lowest, so it will be, the answer will be 800. And you can draw the spectrum and you can see that there is a periodic, so it will be a line spectrum. Okay, and it is given that all the components have a maximum amplitude of 10 volts, so it is a continuously the amplitude will remain same for all the line spectrums. You can try with example this. You have the bandwidth this, middle frequency and peak frequency amplitude this. So you need to draw the frequency domain of the signal. Now the analog part is more or less over. Now come to the digital signal. So I have told you earlier that digital signal, the amplitude is varied into certain levels. Okay, so in the first example is of two level signal, or it can be known as the binary signal. So the amplitude is level 1 and level 2. It is just fluctuating in between these two levels only, and if it is level 2, this is logic 1, and if it is level 1, that is logic 0. In case of multi-level signal, the amplitude is not varied in between just two levels, but it is varied more than two levels, right? In this case, there are 4 levels. So you have this M array, that is 4 array type of signaling, and you can see that if each level is it is having 4 levels, so each level will contribute to 2 bits, right? So in this case, binary case, you have the BPS unit. In 1 second, you can see in 1 second how many bits, 1 2 3 4 5 6 7 8. So in 1 second duration you have transmitted 8 bits, so that's why 8 bits per second is the bit rate. Whereas in this case, how many signaling elements, so in this phase you have one signaling element, another, like this you have how many signaling elements, you have 1 2 3 4 5 6 7 8 signaling elements are there, and each signaling element is contributing 2 bits, so it is creating a bit rate of 8 into 2, that is 16 bps. So you can see that if the number of level is getting increased, the bit rate is getting increased. So these two are the definition of bit rate and baud rate. Is the number of bits per second and the number of signals or signaling element per second. So let's have an example. A digital signal has 8 levels. How many bits are needed per level? We know that if the level are L equal to 8, and we know that L equal to 2 to the power n form, as I have already told you, so you have to calculate n, right? So L equal to 8, so you have number of bits per level equal to 3. Okay, so this is all about the different types of problems. Let's see. A digital signal has 9 levels, and how many bits are needed per level? So basically level 9 is less than 16 and it is more than 8, right? So if level 9, if you put 9 in the previous problem, if you put 9 here, so you will get a fractional value here, right? If you put 9 here, you will get a fractional value here, because number of bits cannot be fractional. So you have to do what? So if it is 9 level, you have to approximate this one. It is less than 16, much nearest highest level is 16. So you can put L equal to 16 and the number of bits will be 4. This is another example. You have a digitized voice signal with a bandwidth of 4 kilohertz, and you need to basically transmit the digitized voice, and what is the bit rate. But the thing is that we used to do sampling when we are doing the analog to digital transmission. The first stage is sampling, and we use the Nyquist sampling theorem, that is the highest frequency of sampling is the frequency sampling is at least twice of the highest frequency present in the signal. So that is the rate of sampling, and whatever is the frequency or the bandwidth here, 4 kilohertz, twice of that, that is the 8 kilohertz would be the at least rate of sampling, and each of the sample is going to represent 8 bits, so 8000 samples per second, and each sample is going to contribute 8 bits. So this is the number of bits per second if you are going to convert a normal analog voice into digitized voice stream. This is another example of bit rate of HDTV. You can calculate this one. So basically we know that in the HDTV you have the aspect ratio 16:9. So we have this 1920 by 1080 pixel per screen. Okay, so if you have this amount of pixel, that is 1920 into 1080 number of pixel per screen, and to have this moving impact, so you need to have the 30 times per second you need to shift the screen, then only it will be a moving, right? So 30 into 1920 into 1080 will be the number of pixel, and it will be in the second, okay, per second. Okay, so 1920 into 1080 into 30, and if it is color bits, then we know that if it's a black and white, so this will be normally 1920, 1080 and 30, but if it is a color, then you have the RGB, right? So there are 3 colors in the color image or pixels. So you have the red, green and blue. So each color is contributing is 8 bits, so 3 color means there's 24 bits, so that's why it's multiplied with the 24. So this 1.5 Gbps is the basically the bit rate of the HDTV. Now come to the transmission impairments. Basically the signal is traveled to the transmission medium, and it is basically whatever we are sending, we are not used to get that same type of signal at the end of the receiver. Okay, so that is the main problem, and the causes are basically attenuation, distortion and noise. So what we know, the attenuation is basically the amplitude of the signal is getting reduced, right? And we can see that if a signal is propagating from, it's not a periodic, it's a periodic kind of signal, it is propagating from point 1 to point 2, suppose. So it is getting attenuated and shifted. So if it is getting attenuated, you need to put some amplifier to, or you can use, in case of digital, you need to have some repeater station in between to regenerate the signal. So here is analog signal, that's why we have used the amplifier in this case. So attenuation is there, and that is natural as far as the transmission medium is concerned. There are different transmission medium, like it can be the twisted pair cable or coaxial cable or optical fiber cable, but uh, you have the different amount of attenuation as far the transmission medium is concerned. So in this case, let's have one example. Suppose we have a signal transmitting through a transmission medium, and you can see the power at the receiver end P2 is going to be half of the transmitted power P1. So what is the attenuation? Attenuation is basically in terms of dV, if we represent, so it is 10 log base 10 P2 by P1. So if the question is like this, the P2, the received power is going to be half of the transmitted power, so it will be 10 log base 10.5, it is minus 3 dB. So if you have half of the power you are getting at the receiver, basically 3 dB loss or minus 3 dB gain, you can say in this case, right? Another example, a signal is traveling through an amplifier, and you can see that if the transmission medium it will loss, and if it is passing through one amplifier you have some gain in between. So if the received signal is P2 and that is 10 times of P1, okay, so in this case the amplification will be there instead of the loss, and the formula remains the same. Okay, so you can see the P2 is 10 times of P1, and if you equate this one you have this plus 10 dB loss. So what are the different types of questions? So if you have a negative gain, that means it will be a loss, and if the gain, this value is positive, that means there is some amplifier to do the amplification part. So another question is there. So if you have different types of combination of transmission medium, and each medium is basically contributing some amount of loss, and you have an amplifier that is giving some amount of gain, so it's a mixed type of system with the two transmission mediums and between amplifier. The question is, what is the total loss or gain? So what you have to do, the values are given, this is minus 3, 7 and minus 3 again. So these values can be changed also as far as the design is concerned, and you can calculate the total loss or gain in terms of dB. Okay, so go through another problem. So the thing is that the loss in a cable is usually defined in decibel per kilometer, right? So dB per kilometer, it's not only dB. The thing is that the signal at the beginning of a cable is minus 0.3 dB per kilometer, and this initial power is 2 milliwatt. So what is the power of the signal after 5 kilometer of distance? So basically we know that the loss is, cable loss is 0.3 dB per kilometer. So after 5 kilometer you are supposed to have a loss of minus 1.5 dB. So if you have this minus 1.5 dB with you, and you know that P1 is 2 milliwatt, so you need to calculate P2, and the answer is 1.4 milliwatt. Next thing is distortion, that is another type of impairment, and you can see that if you know that the ideal digital signal is having a bandwidth of infinite, and even it is transmitted through a physical medium, so it is decomposed basically into a fundamental sign and its harmonics. So now what happens when it's passed through the medium, each of the harmonics face a different phase lag, so ultimately when it is arrived at the receiver it is combined, and you can see different types of aberrations or different types of what can I say, that different types of distortions is if you are combining. So it is a transmission between traveling suppose 1000 kilometer. So when it is again combined, it is distorted kind of signal you are getting instead of the pure digital signal you have transmitted. So this is the thing that happens here. Okay, so this is about the distortion, and last thing is the noise part. There are different types of noise, and what is noise? Noise is basically the unwanted signal which is superimposed on the main signal. Different types of noise are there, like thermal noise, you have the induced crosstalk impulse noise, flicker noise, all these types of noises are there. And there are different basically different sources for creation of this noise. For example, if you have the thermal noise, the main source is the random motion of the electron in the wire. That is the reason that due to which the thermal noise is created at the transmitter part. Okay, now if you have a signal or a system, so if you have the system, you need to find out whether the system is uh, good or not, right? The receiver system is good or not. So what is your criteria as a design engineer or as a system engineer? You have to have a system with a better SNR. What is SNR? SNR is the signal to noise ratio. Okay, signal to noise ratio, and signal power divided by noise power is the expression of the SNR. Okay, so basically this is unitless, but many of the cases we actually do the conversion in dB and we get the value of SNR in decibel.